All right, Algebra 1, welcome back. Let's jump right back into things. Hope everyone's doing well. Modules. All right, this should be a brief lesson today. Let's see. So we've already done experimental and theoretical probability, geometric sequences. That was last class. And so today is exponential growth and decay. So I'll briefly fly through this. And then you guys we'll just jump straight into those problems just to make that even easier. How's that look? Nice. Okay, so let's see. Okay, exponential decay. Let me frame this a little bit better so we get more space. Nice. All right, hopefully you can see that. Okay, so exponential growth and decay. So we've looked at that. We've looked at this a little bit before. This shouldn't be completely new to you. So it says that it's very similar to geometric sequences, although instead of finding a pattern and a common ratio, we'll be expressing ideas in the form of an equation. Okay, very cool. This makes sense. Now, you guys, whether or not you've realized it or not, you've seen this before. So you've seen it in this form. F of x equals a times b to the x. Now, you've not seen it like this, right? But you have seen it in a very similar way. So let's take a look. You've seen something like this. Let me show you one that you probably have seen. So f of x is like x. Let's say like 2 to the x. That's a classic one. There's also like 3 to the x. This would be pretty classic. And so these are our b values, clearly. And I don't believe you get into it in this course, but you will in the next one. But they could play around with some coefficient out front. So notice that the a value in each of these examples, right, the b value is equal to 2. And the b value here is equal to 3. So this is our growth factor, right? It's positive growth. And the a in front of it is actually a 1, even though it's not written, right? So each of these have been a value is equal to 1. But a doesn't have to be equal to 1. It could be like 2 times 2 to the x. Cool, but that's going to be for another course. You'll see that much later. I just wanted to kind of show you the general ideas going on. Okay, so it's much easier than this, and we'll define all this and write it all up for you. But remember the general equation. I'll leave it up here at the top. F of x is a times b to the x. Okay, there that is. Here's our very first example. It says the population of ants can be modeled by the function 2 times 3 to the x. Okay, interesting. So 2 times 3 to the x. So our a value, this is a, this is b, and that's our x, our unknown. And it says x is the number of days that pass as our population grows. Okay, so that tends to mean that these ant populations are going to grow exponentially. You've probably heard this language. You probably heard a lot of this with what's going on currently, talking about exponential growth. So this shouldn't be anything new to you. So that's the language we're going to use here, exponential growth. And so our ant population here is modeled by exponential growth. And it says, what will the population be after the 6th day? So if we know that x is the number of days, let me write days out here next to it, then we know that what? We could say f of 6, right, would be equal to 2 times 3 to the 6th power, which is, of course, what? You could put that in a calculator, and you could say 2 times 3 to the 6th power, that's like 2 times 729, and you can see their answer here is some 1,458 ants. So these ants are going crazy fast. Now, that was just kind of a random example, but let's not do one that's so random. Let's do one that really makes sense so you can really see. So what happens at day 0? How many ants do we have? Let's play around with that. So 2 times 3 to the 0th power. And of course, anything to the 0th power is just 1. So on the 0th day, we have 2 ants. So that means this population is starting with 2 ants. And then how about on the first day? How many ants do we get? So this would be 2 times 3. So on the first day, right, we get 6 ants. So we went from 2 ants to 6 ants. Cool. How about on the second day, what do we get? So now notice how this works, and I just like to really play this out so everyone really gets this. It would be 2 times 3 squared. That's another way of saying what? Times 3. Cool. So 2 times 3 times 3. So the first day was just what? 2. Or excuse me, the 0th day was 2. The first day was 2 times 3. And the second day was 2 times 3 times 3. So you'll notice the pattern here, we're just doing repeated multiplication. So the third day would be 2 times 3 times 3 times 3, and etc. on and on and on. Cool. And the sixth day is 2 times, and then 6 of those 3s in a row. All right, next up, population of tigers in the wild decreases. Now, this is more rare, but it does happen in animal populations. So a rapid decrease in population. So this is going to be decay. The language they use is decay. So, and they give us the function, let me switch colors. They give us the function f of x is 3,000. Notice we start with this first number. This a value is kind of what the population starts with. So that means we start with 3,000 tigers. And then here's our growth factor, 0.95. And then this is going to be the number of days again. In this case, it's not days, but it represents years. Cool. So the population of tigers is 3,000, and they're slowly dying of some form by 5%. Can you see how this is less than 1? So now, this should lead you to a lot of understanding about growth and decay. So if this number right here, this b value, if this b value is greater than 1, it means you're growing. And if this b value is less than 1, in this case it's 5% less than 1, right, it is dying. So this is another way of saying that every year we lose 5% of the tiger population. Cool. And so let's read what they want. To solve this, substitute x into the equation. Right, they want to know what is the population of tigers? What will it be in 10 years? So that's what that says. Good. So here's this 10 years bit of this. So what do we do? If we know that's the x value, all we do is just plug that in. F of 10 is our 3,000 tigers. After 5% of the tigers dying every year for 10 years, what will our population be? Okay, this is not complicated, whatever this is, right? You would plug this into a calculator and just solve it. So it looks like it's 3,000 times, and 0.95 to the 10th is 0.6, which means they have 60% of their population remaining, or they lost 40%. Cool. So that comes out to 1,796 tigers. How appropriate. Let's talk about tigers. All right. Okay, so loss of population. That's how that looks. So that's, of course, called decay. When you lose things, it is decay. When you grow things like money, it is called appreciation or growth. Okay, example 2, exponential growth. Let's write things out. Now, just like they said before, we're going to be writing things out with particular equations. So now they're giving us a nice equation for exponential growth. And this is going to show now a rate of growth. So this makes sense, kind of, right? Let's write this out. So it gives you a function like you're used to seeing. So y equals some a, some starting point, times 1 plus some rate to the t. And t is, of course, some time. And 1 just means it's going to be larger than 1, right? And so we're adding some growth factor that's going to be definitely larger than 1, right? And this will cause this to grow, right? At some rate r. Cool. And this is over some time t. So this could be years or minutes or whatever you want the time to be, whatever time scale it's in. So let's take a look at that. So this is the most important distinction of exponential growth is that the value being raised to a power, the value in the parentheses, has to be larger than 1. Okay, that's the key here. So clearly it will be larger than 1. The original value of the sculpture is $1,400. The value is increasing by 4% each year. Write the exponential growth to represent this. Okay, easy enough. So this is our initial amount, initial value. So our initial value is $1,400, right? So it says the original value of the sculpture is $1,400 times 1 plus its growth value, 4%, 0.04. And this is our x up here, or the unknown. I can leave it as a t because this is a financial problem. So now it says write a exponential function to represent and find the value of the sculpture after 20 years. So they want to find it at t equals 20. So y equals 1,400 times 1.04 to the 20th power. Okay, now these are largely calculator problems. So you would just plug this into a calculator and you'll have access to that for this quiz if you need it. You can see it right here, 1,400 times 1 plus 0.04.